Good morning friends. I am Atiq Rahman. I teaches at the Department of Geography, Jamia Millia Islamia, New Delhi. This morning we are going to discuss and understand a module which is very important for the remote sensing, and the title of this module is Electromagnetic Radiation, that is EMR, is interaction with the atmosphere and earth surface features. As we know, and you must have learned in the previous module, that it is the sun's energy which is being used for remote sensing, and that is the optical remote sensing. So, what happens that sun's energy travels from far off and it reaches the surface of the earth. Before reaching the surface of the earth, it interacts the energy of the sun in the atmosphere, and after interacting in the atmosphere, it comes and reaches the surface of the earth, and after reaching the surface of the earth, again it goes back and travel through this space and reaches the sensor which are placed on a remote sensing satellite. So, what happens? Three things happens. One is interaction of sun's energy in the atmosphere, then interaction with the earth surface feature, and then back to space at the sensor, and again it interact with the atmosphere. So, in this process the sun's energy interacts twice the atmosphere and once the earth surface feature. So, therefore, the learning objective of this module is to understand what happens the sun's energy when it interacts with the atmosphere and earth surface features. So, we all know from the very beginning, from the school time, that in the atmosphere we do have dust particle, we do have pollutants, we do have water vapor and many other things. So, what we have, these dust particles and water vapors are in different size and so and so. So, it has an important role when the sun's energy interact with it, and when it reaches the surface of the earth, again three things happens. One is that it reflects back the energy, some portion of it, some portion of the energy is absorbed by the earth surface and it gets transmitted in the material on the surface of it, and some of the energy is absorbed, and after absorption what happens, it emits slowly. So, whatever the energy that has travelled and reaches the surface of the earth, it has to balance either through any of these three medium: reflectance, absorption and emission. So, in this module we are trying to understand this, and what happens that the sun's energy, as you already know, that the sun's energy travel and that reaches the surface of the earth in different region of the spectrum, and we all know that I must tell you that about 40% of the sun's energy reaches the surface of the earth in the visible region. Remaining 50% of the energy that reaches the surface of the earth is in the form of electromagnetic, that is in the form of in the infrared region. So, 40% in the visible region, 50% in the infrared region, 9% in ultraviolet region, and 1% is in X-rays, gamma rays, radio wave and so and so. So, dear friends, we are especially in the field, in open skies. Why? I just wanted to let you understand and see the natural open air, where we have the atmosphere, we have the sun above it and we have the ground. So, we want to understand the interaction of these three: sun's energy which is travelling through the space, we have the space, in the space we have different water vapors, dust particle, pollutants and other things, and the surface of the earth. On the surface of the earth we have different surface features. We have the grasses, we have the soil, dry soil, we have the trees behind me and many other things. So, all these these features interact, this sun's energy interact with these features. So, this was a main motive and the basic idea while talking to you in the open skies. Now, let us go to the field and to understand through the diagrams and the pictures how this interaction and how it looks like and how these features interacts and what happens, what are different physics behind it. So, let us go to the classroom. So, dear students, while from field to classroom, let us understand the issues what we are talking outside. We are talking about the sun's energy interaction with the earth's surface feature and the atmosphere. So before reaching the surface of the earth, it interacts with the atmosphere. In atmosphere, there, as I said before, there are dust particles, then pollutants, as well as water vapor. So what we have, when the sun's energy strike all these surface atmospheric surface feature, it scatters, the sun's energy scatters. The scattering of the sun's energy from the atmosphere takes place in two ways. One is called selective scattering, and another is called non-selective. Within the selective scattering, we have mild scattering, and second is called ray light scattering. Now, before understanding these two types, selective and non-selective scattering, there are other issues, there are factors which leads to scattering of light. One is that is called abundance of the particles. The particles what we have, dust particles, pollutants and water vapor. Then we have the size of the particle. And the third is wavelength radiation and the wavelength region. And the fourth is how much area is covered with these particles, that is the depth of the particles. Now let us understand all these things, selective and non-selective and other phenomena, through table. And we can clearly see in the table 1 that shows in selective scattering, ray light scattering takes place at the wavelength, that is lambda by 4. The mild scattering takes place at the wavelength lambda to lambda by 4. The approximate dependence particle size in the ray light scattering, when the particle size is less than 1 micrometer, and in mild scattering the particle size is 0.1 to 10 micrometer. In non-selective scattering, that takes place within the wavelength region of lambda, and the approximate particle size is more than 10 micrometer. Now, what are these particle size means, what all these could be? So, in the ray light scattering, the particle size which is less than 1 micrometer is, for example, air molecules. In the mild scattering, which takes place because of the smoke and haze, which has a particle size of 0.1 to 10 micrometer, and in the non-selective, the particle size is more than 10 micrometer, which includes what are different kinds of particles, that is dust, fog and clouds, etc. Now, the sun's energy after interacting the atmosphere, it interacts with the atmosphere, then it reaches the earth's surface. So, after reaching the earth's surface, it reflects back towards the sensor, again back to the atmosphere. So, what we have, when it reaches the atmosphere, before that when it interacts the surface of the earth, it reflects. So, a reflection of the energy takes place in different ways, So, that depends what kind of reflection will take place, what will the nature of reflection, that depends upon what kind of surface it is. In the ground, what we have, there could be one surface which could be very straight, there could be one surface which has certain grasses, short grasses like this, there could be one surface, another surface of the earth where could be some trees, short trees or the tall trees. There could be another surface where we have the very short trees, with tall trees, canopies, and so and so. So the energy which is coming from the sun, when it strikes the surface of the earth, it behaves differently. It behaves differently on all the surface of the earth. So let us understand the reflectance, reflective properties and behavior of the sun's energy through diagram. And for that, if you see the figure 4 of this module, what we have, figure 4a, that is the surface which I was talking about, is a perfect specular reflector, where the earth surface is smooth, and earth cannot be so smooth because it is a natural surface where we have undulation. We do not have a smooth as what we have the table or the glass floor and the marble floor and so and so. So what we have on the natural surface of the earth, we have the smooth surface that we take as a water, surface of the water, which is quite smooth. So what we have, if you see this, the angle of incidence will be the same of angle of existence. If on a smooth surface, if the angle of incidence of the sun's energy is 45 degree, 35 degree or 55 degree, the angle of existence will be same. That we call is a perfectly specular reflector. The figure 4b shows that near perfect specular surface, which I showed you that the grasses. There are short grasses, what we have, the angle of incidence, if suppose angle of incidence is 45 degree, what happens, since there are different objects at a very short distance, so what will happen, there will be a lot of reflectance from these small cones and small grasses. So what will happen, the light will diffuse in different direction, with a different amount. Now the third figure, that is figure 4c, that shows near perfect diffuse reflector. What will happen, the incidence energy will be reflected and will be redirected, rediffused in different direction. That will be redirected, rediffused in all the direction, because suppose if we take the trees which has this canopy, so energy which will come, some will go to right, some will go to left, some will go to east, some will go to west. That kind of reflection is called a near perfect diffuse reflector. And the fourth last, that is called the perfect diffuse reflector or Lambert surface. This is known as a Lambert surface or perfectly diffuse surface because it is one of the which where the radiant flux leaving the surface is constant for all angle of the reflectance to the surface, which is normal. So there are 4 types of reflectance that we observed commonly on natural surfaces on any parts of the earth. So we were discussing the issue of selective scattering, which is of 2 types, raylight and Mie scattering. So if I explain you in text, that will not give you clear understanding. To have a very clear and fair understanding of raylight scattering or Mie scattering, let us see the figure 1. Figure 1 shows the raylight scattering, the example of raylight scattering and Mie scattering. What we have, if you see the Mie scattering, which is the particle size is small, whereas in the raylight scattering the particle size is large. So what happens, raylight scattering is dominant, the Mie scattering intensity that is projected outward. Since the raylight scattering is strong in the short wave, so we have different scattering in all the direction, whereas in a raylight scattering what we have, the particle size is big, so diffusion and the scattering of the light is for a longer distance in a more dispersed way. But if you see the figure 2, that talks about the non-selective scattering, as I showed you in the table, that a non-selective scattering takes place when the particle size is big, dust particle or any other particle, and especially the cloud. So if you see this, the large part of cloud, if the sun's radiation comes and there is large pockets of clouds, so from that cloud what we see from the figure 2, that clearly shows that on the both side, right and left, that a non-selective scattering takes place. So, that gives you very clear understanding about the selective and non-selective scattering. So, to give a good summary of selective and non-selective scattering, what we have seen in the table, that is the particle size and wavelength region. So, what we have, if we see the table, compare the table with the figure 5, what we find that in figure 5, that gives you very clear understanding of selective and non-selective scattering, which clearly shows the particle size and wavelength region through graphs. So, let us see figure 3. If you see the figure 3, that shows the atmospheric scattering. The figure 3a shows ray light scattering, where I have shown you a gas molecule which is very small. On the right side, if you see the wavelength, wavelength is a short wavelength. If you see 3b, the Mie scattering, where the diameter is little bit big, and the example is that of, as I have told you before, is a smoke and dust. If you see the wavelength region is further almost same or little bit more than the first one. The third, that is a non-selective scattering, is a big circle, and that is a water vapor. You do not feel that water, the particle size of the water is so big, but to give you a better understanding, it has been represented in a big circle. If you see the right side, that is a wavelength region. So, that is a photon of electronic energy moduled as a wave, because all the energy travel and move in the form of wave. So, that I hope that from this figure 3, it has become very clear what all scattering is there, what are different types of scattering that takes place in the atmosphere when the sun's energy travels through the atmosphere to reaches the surface of the earth. So, friends, moving further in this module, let us understand some other issues, that is a spectral reflectance curve. This is very important in the remote sensing. If I explain you what is this, it is nothing but is a incident energy and the reflected energy. So, how much energy is coming, reaching the surface of the earth, and how much energy is reflected back. This is very important in order to understand, in order to distinguish, separate out different objects differently. As I said in the earlier module, and you must have also studied, that we need to know how much energy is coming and how much energy is reflected back, and this energy is precisely recorded at the sensor. Now, we have seen that there is a spectrum, electromagnetic spectrum. So, different energy, when it crosses the spectrum, reaches the surface of the earth in different way. When it goes back and again it crosses, it reaches the sensor, this is another norm. So, there is a difference between the incidence and the reflected energy. So, this is we need to understand, and to understand this we need to understand, we can understand it clearly in the figure 5, because different objects behave differently, that I have already told you before. So, let us see figure 5 that it gives you very clear understanding. Now, figure 5 shows that if you see the wavelength region 0.5, where we have different objects, say for example artificial turf, asphalt, fallow land, then we have sandy loam soil, then we have the concrete, then we have the grasses and the water bodies, clear water bodies and the turbid water bodies. So, if you see the region 0.5 micrometer, on the left side on the y axis we have the reflectance in percentage. So, what it shows that in the blue region the reflectance is not so high, but if you go to green and red region and infrared region, the reflectance increases for all the objects, whether it is a concrete, whether it is a grasses, whether it is a snow field, whether it is the sandy loam soil and so and so. The moment you go to 0.7, the grasses reflect very strongly, concrete further reflects strongly, sandy loam also reflects strongly, but at the same time the clear water bodies does not reflect strongly. That means, in this region, in region 0.7 and 0.8 there is a lot of absorption, and therefore, I must have shown you, and you have already seen that in this infrared region the water looks black in the false color composite satellite image. Now, if you see figure 6, that is the electromagnetic spectrum, because I was talking about how the sun's energy interact with the atmosphere and then it reaches the surface of the earth. So, there are certain regions. If you see the left side region and the right side region, there are different spectral range. On the left side we have the shorter wave region, on the right side we have the long wave region, and in between we have the visible region, which clearly shows 0.4 to 0.7 micrometer. On the right side of it we have the reflective infrared, thermal infrared. So, what we have, if we see this figure 6, that clearly shows that there is a dark patches in it and there is a clear patches in it. The dark patches are blocked, that you must have also studied in the earlier module, that is the blockages. Blockages by oxygen O2 on the left side in the region 0.1 to 0.3 micrometer. If you go right side, we have blockages from H2O, water vapor, carbon dioxide, then carbon dioxide again in the region 3 to 5 micrometer somewhere. Then we have blockages by H2O from 5 to 8 micrometer. Then further on we have the blockages in the region 15 to 30 micrometer, that is by the CO2. So, all these gases, dust particle and water vapor, they are blocking the spectrum. The energy is not traveling in this region to the surface of the earth. Therefore, in this region the remote sensing cannot be done, that cannot be performed, because they are opaque. But the rest of the region that you see from this figure 6 is open to sense a particular part of surface of the earth, and therefore you must have also known by now that these are the region that is called atmospheric window. Now, we come to the last part of the today's lecture, that is a refraction. We all know what is a refraction, but in remote sensing we try to see the refraction that once a light passes from one source to another place, it crosses through different medium. So, what we have, suppose a light is traveling from the sun, it crosses the atmosphere. Atmosphere is little dense. If you come below this and reaches the surface of the earth, the atmosphere becomes little more dense, and when it reaches the surface of the earth, so this is another medium. So, it is open, but this is the solid crustal mass of surface of the earth. So, once it strikes this particular surface of the earth, the angle of the sun's incidence changes. That means, if I show you here, if the light is passed from this place, so this is light, that is air, then we have the water, then we have the glass. So, what we have at every stage, what happens, the angle of the incident sun gets changes. So, refraction is precisely what we have. Since the sun's energy, which is traveling from the sun, reaches coming to the surface atmosphere, and then at the surface of the earth, and then again goes back. So, from sun to earth and back to sensor, there are three medium: light, and then solid earth surface, and again the lighter medium. So, that also takes place. So, this is another very important issue that one need to understand, the refraction. Another issue that could be probably the last is the contrast. What happens that since the optical remote sensing uses sun's energy, so when we have the atmosphere full of dust particle, gases, water vapor, clouds, so there is a poor contrast. So that means the object which is there on the surface of the earth cannot be detected clearly. So for that, to increase the contrast, we have different techniques, various models, algorithm. In the digital image processing, there is another field that we call is a DIP, digital image processing software, where we can go and use the contrast in stretching, contrast enhancement technique to make the satellite data in a much better way so that we can extract the information more clearly, more precisely. So that is the another issue that need to be dealt separately in a digital image processing technique. So dear students, let us summarize the today's module, today's lecture. To summarize and to put it in brief, what we have seen in the last half an hour or so, that the energies interaction with the atmosphere and the surface of the earth. So in this process, scattering takes place, absorption takes place, reflectance takes place, and so and so. So we have seen very clearly, we have I have demonstrated you that how the scattering takes place, what is the factor on which the reflectance and absorption in the earth atmosphere takes place, what are the factors, what are different dust particles, what are different size of the particles which are responsible for different scattering. So we have seen that there are two types of scattering, one is selective and second is non-selective. In that we have, in the selective we have rare light scattering, we have the Mie scattering. So that is precisely depend upon the size of the particle, the amount of particles, the abundance, its characteristics, the volume, depth and aerial extent. So all these are we have understood in this module, and this is very important in a sense that if you try to capture any part of surface of the earth, we need to see whether this atmosphere is clear, whether it is dusty. In the summer season, the satellite data which is capturing are not so good. In the rainy season, the satellite data when we are using the optical region is not so good because of the abundance of water vapor. We have also seen in this module what are the different spectral regions in which the sensing takes place, especially the optical remote sensing. So I do hope understand that you may have got a very clear cut and easy understanding of the EMR radiation, its interaction in the atmosphere and the earth surface feature. I do hope that it will be very useful for your further learning in the remote sensing. Thank you very much, and thank you for your kind attention. Thanks all.